Introduction to 6RD. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are exploring 6RD, which stands for IPv6 Rapid Deployment. This is a critical transition technology that service providers use to enable IPv6 connectivity over existing IPv4 infrastructure. Think of 6RD as a bridge between the old and new Internet protocols. It is particularly valuable for Internet service providers who want to offer IPv6 services to their customers, but have not yet upgraded their entire backbone network to native IPv6. The technology was standardized in RFC 5969 and represents an evolution of earlier transition mechanisms. The fundamental challenge that 6RD addresses is simple but significant. How do you provide IPv6 connectivity to end users when your provider network still operates primarily on IPv4? Many ISPs have millions of dollars invested in IPv4 equipment and infrastructure. Replacing all of this overnight is neither practical nor economically feasible. 6RD provides an elegant solution by encapsulating IPv6 packets inside IPv4 packets, allowing them to traverse the IPv4 network transparently. This means the IPv6 traffic from customer premises can reach the IPv6 Internet without requiring every router in the provider's network to understand IPv6. What makes 6RD particularly interesting is its stateless nature. Unlike some other transition technologies that require maintaining connection state or translation tables, 6RD uses a deterministic mapping between IPv4 and IPv6 addresses. This means there is no need for complex databases or synchronization between different network elements. The mapping is mathematical and automatic, which significantly reduces operational complexity and improves reliability. Every customer gets their own IPv6 prefix that is derived from their IPv4 address, and this relationship is maintained consistently throughout the network. How 6RD works. Let's dive into the operational mechanics of 6RD to understand exactly how it enables IPv6 connectivity. At its core, 6RD creates a tunnel between the customer premises equipment, which we call the customer edge or CE router, and the provider edge or PE router at the ISP. This tunnel carries IPv6 packets wrapped inside IPv4 packets. Think of it like sending a letter in an envelope inside another envelope. The inner envelope contains the IPv6 addressing information, while the outer envelope uses IPv4 addresses to traverse the provider's network. The process begins at the customer's location. When a device on the customer's network wants to communicate using IPv6, it sends an IPv6 packet to the CE router. The CE router is configured with 6RD, and knows it needs to encapsulate this packet. It takes the entire IPv6 packet, including all headers and its payload, and wraps it inside an IPv4 packet. The IPv4 source address is the customer's public IPv4 address assigned by the ISP, and the destination is the address of the border relay, which is a PE router at the edge of the provider network. The protocol number in the IPv4 header is set to 41, which specifically indicates that this packet contains an IPv6 payload. As this encapsulated packet travels through the provider's IPv4 network, all the intermediate routers see it as a normal IPv4 packet. They don't need to understand IPv6 at all. They simply route it based on the outer IPv4 headers using their existing IPv4 routing tables. This is the key advantage of 6RD. It leverages existing infrastructure without modification. When the packet reaches the border relay, the PE router strips off the outer IPv4 header, extracts the original IPv6 packet, and forwards it onto the native IPv6 Internet. The reverse process happens for incoming IPv6 traffic destined for the customer. IPv6 prefix delegation in 6RD. One of the most important aspects of 6RD is how it handles IPv6 address assignment through an automatic prefix delegation mechanism. Unlike traditional IPv6 deployment, where addresses might be manually configured or assigned through DHCP v6, 6RD uses a deterministic algorithm that embeds the customer's IPv4 address into their IPv6 prefix. This creates a unique, predictable relationship between the two address spaces. Here's how it works mathematically. The ISP first allocates a large IPv6 prefix for their entire 6RD deployment, typically a /32 or larger. Let's say they use 2001:db8::/32 as their 6RD prefix. They then define how many bits of the customer's IPv4 address will be embedded into the IPv6 prefix. In many cases, the entire 32 bits of the IPv4 address are used, but if the ISP's IPv4 addresses share a common prefix, those common bits can be omitted to save space. For example, if all customers have IPv4 addresses starting with 203.0.113, those first 24 bits are redundant and don't need to be encoded. The CE router performs this calculation automatically. It takes its assigned IPv4 address, converts it to binary, and inserts those bits into the designated position within the 6RD prefix. The result is a unique IPv6 prefix for that customer, typically a /56 or /64, depending on configuration. This prefix is then used for the customer's entire IPv6 network. The beauty of this system is that it requires zero state on the network. Any router can calculate the IPv6 prefix for a given IPv4 address, and vice versa, using only the 6RD parameters, which are distributed through DHCP or static configuration. This automatic prefix delegation also means customers can be provisioned instantly. When a new customer connects and receives an IPv4 address through DHCP, they simultaneously and automatically get IPv6 connectivity through 6RD. There is no need for separate provisioning systems or databases. The mathematical relationship between the addresses means everything just works. This significantly reduces operational overhead for service providers and enables rapid IPv6 rollout. 6RD configuration parameters. To successfully deploy 6RD in a network, several key parameters must be configured and distributed to customer equipment. Understanding these parameters is essential for both implementing and troubleshooting 6RD deployments. These parameters define the mathematical relationship between IPv4 and IPv6 addresses and tell the CE router how to perform encapsulation and address calculation. The first and most important parameter is the 6-road prefix itself. This is the IP6 prefix that the ISP has allocated for their entire 6-road deployment. It is typically a /32 prefix, but could be larger or smaller depending on the provider's IP6 allocation. Every customer's IP6 prefix will be a subset of this larger prefix. The 6-road prefix must be carefully chosen to avoid conflicts with other IP6 allocations the provider might have, and it should be sized appropriately to accommodate all customers. The second critical parameter is the IPv4 mask length, often called the common prefix length. This tells the CE router how many bits at the beginning of the IPv4 address are common across all customers and therefore do not need to be embedded in the IPv6 prefix. For example, if the ISP uses the 203.0.113.0/24 block for all their customers, the common prefix length would be 24, and only the last 8 bits of each customer's IPv4 address need to be embedded. This is important for efficient use of the IPv6 address space, as it determines how many bits of the customer's IPv6 prefix are available for their own subnetting. The third essential parameter is the border relay IP version 4 address. This tells the CE router where to send encapsulated IP version 6 packets. The border relay is the PE router that will decapsulate the packets and forward them to the native IP version 6 internet. ISPs typically deploy multiple border relays for redundancy and load distribution. Though the basic 6RD specification allows for only one to be configured via DHCP, these parameters are usually distributed automatically through DHCP option 212, which was specifically defined for 6RD, though they can also be statically configured on CE routers for testing or special deployments. Border relay operation. The border relay, sometimes called the BR or 6RD relay, is a critical component in the 6RD architecture. It sits at the edge of the ISP's network and serves as the gateway between the IPv4 provider network and the IPv6 Internet. Understanding its operation is key to grasping how 6RD enables end-to-end IPv6 connectivity despite an IPv4 core network. When the border relay receives an IPv4 packet with protocol number 41, it knows this is an encapsulated IPv6 packet from a 6RD customer. Its first task is decapsulation. It strips off the outer IPv4 header to reveal the original IPv6 packet inside. This IPv6 packet contains source and destination IPv6 addresses. The source address will be from the customer's 6RD derived prefix, which means it embeds the customer's IPv4 address. The destination will be some address on the IPv6 Internet. The border relay then forwards this IPv6 packet onto its native IPv6 interface using standard IPv6 routing. The reverse path is equally important and slightly more complex. When an IPv6 packet arrives at the border relay from the Internet destined for a 6RD customer, the border relay must determine which customer should receive it and what IPv4 address to use for encapsulation. This is where the stateless nature of 6RD shines. The border relay looks at the destination IPv6 address and extracts the embedded IPv4 address from it using the known 6RD parameters. It then encapsulates the IPv6 packet in an IPv4 header with this extracted address as the destination. Because of the deterministic address mapping, the border relay knows exactly where to send the packet without maintaining any state tables. Border relays must be strategically placed in the network topology. They need excellent connectivity to both the IPv6 Internet and the ISP's IPv4 network. Many ISPs deploy multiple border relays for redundancy and to distribute load. The relays also need to be announced via anycast routing so that outbound traffic from customers naturally flows to the nearest available relay. Performance characteristics are important too. The relay must be able to handle high packet rates for encapsulation and decapsulation, and it should have minimal latency to avoid degrading the customer experience. Modern implementations often use specialized hardware or optimized software to handle these operations at line rate. 6RD address calculation example. To truly understand 6RD, it helps to work through a concrete example of how the address calculation works. This mathematical process is what makes 6RD stateless and automatic. Let's walk through a realistic scenario step by step to see exactly how an IPv4 address gets embedded into an IPv6 prefix. Imagine an ISP has been allocated the IPv6 prefix 2001:0DB8:32 for their 6RD deployment. They have decided to use their entire IPv4 address block 203.0.113.0/24 for 6RD customers. Since all customer addresses start with 203.0.113, those first 24 bits are common, so the IPv4 mask length is set to 24. A specific customer is assigned the IPv4 address 203.0.113.45. Now let us calculate their IPv6 prefix. First, we identify the variable part of the IP version 4 address. With a mask length of 24, the first 3 octets are common, so we only need to embed the last octet, which is 45. Converting 45 to binary gives us 00101101. This 8-bit value needs to be inserted into the IP version 6 prefix. The ISP's 6RD prefix is 2001:0DB8::/32, which means the first 32 bits are fixed. The next bits will be the embedded IP version 4 information. Now we construct the customer's prefix. We start with beginning with 20 ending with 01 beginning with 0D ending with B8, which is the first 32 bits. Then we append the 8 bits from the customer's IPv4 address, beginning with 00 ending with 01. In hexadecimal, this becomes 2D. We need to pad this to fill complete hexadecimal groups, so the prefix becomes beginning with 20 ending with 01 beginning with 0D ending with B8 beginning with 2D ending with 00:/40 if we are giving /40 prefixes to customers. However, more commonly, ISPs extend this to a /56 or /64 for customer delegation, which would be beginning with 20 ending with 01 beginning with 0D ending with B8 beginning with 2D ending with 00:/56 or beginning with 20 ending with 01 beginning with 0D ending with B8 beginning with 2D ending with 00 beginning with 00 ending with 00:/64. The exact length depends on how much subnetting capability the ISP wants to give customers. This calculation happens automatically in the CE router. When it receives the 6RD parameters via DHCP option 212, it knows the 6RD prefix, the IPv4 mask length, and its own IPv4 address. It performs this exact calculation and immediately starts advertising the resulting IPv6 prefix to devices on the customer's network via router advertisements. The reverse calculation is equally important. When the border relay sees an IPv6 packet destined for 2001:0DB8:2D00:1234, it extracts the 2D from the prefix, converts it to decimal 45, combines it with the common prefix 203.0.113 to get 203.0.113.45, and uses that as the IPv4 destination for encapsulation. Comparing 6RD with other transition technologies. To appreciate the strengths and appropriate use cases for 6RD, it is valuable to compare it with other IPv6 transition mechanisms. Each technology was designed to solve specific problems, and understanding these differences helps in choosing the right tool for a given situation. Let us examine how 6RD compares to some of the most common alternatives. First, consider 6-4, which was one of the earlier automatic tunneling mechanisms defined in RFC 3056. Both 6-4 and 6RD use IPv4 Protocol 41 encapsulation and derive IPv6 prefixes from IPv4 addresses. However, there are crucial differences. 6-4 uses a fixed well-known prefix, 2002::/16, and embeds the entire public IPv4 address into the next 32 bits of the IPv6 address. This means anyone with a public IPv4 address can automatically get IPv6 connectivity through 6-4, which sounds great in theory. In practice, 6-4 suffered from serious problems. The relay routers were often operated by volunteers and unreliable, path selection was unpredictable, and there was no accountability or quality of service. ISPs couldn't control the customer experience. 6RD was explicitly designed to address these shortcomings of 6-4. The key difference is that 6RD is provider-controlled. The ISP allocates their own IPv6 prefix instead of using the well-known 2002::/16 prefix, and they operate their own border relays. This means the traffic stays within the provider's network, path selection is deterministic, quality of service can be maintained, and the ISP has full visibility and control. The other major improvement is that 6RD allows for IPv4 prefix compression, If all customers share a common IPv4 prefix, those bits don't need to be embedded, which provides more bits for customer subnetting. This makes 6RD much more practical for real ISP deployments. Now let's compare 6-Road to Dual Stack Lite, or DS-Lite, which is another popular transition technology defined in RFC 6333. DS-Lite also uses tunneling to carry traffic over the provider network, but it works in reverse from 6-Road. In DS-Lite, the provider network runs native IPv6, and IPv4 traffic is tunneled from the customer through the IPv6 network to a carrier-grade NAT. This makes sense for providers who have already upgraded their core to IPv6 but still need to support IPv4 customers. In contrast, 6-Road assumes an IPv4 core and tunnels IPv6 traffic. The technologies are complementary. An ISP might use 6-Road during their initial IPv6 rollout when the core is still IPv4, then later migrate to DS-Lite after upgrading to a native IPv6 core. Teredo, defined in RFC 4380, is another tunneling mechanism worth comparing. Teredo was designed specifically for end users behind NAT who want IPv6 connectivity without ISP support. It uses UDP encapsulation instead of Protocol 41, which allows it to traverse NAT devices that might block Protocol 41. However, Teredo requires complex NAT traversal procedures and server infrastructure, and it provides relatively poor performance. 6RD, being ISP operated, does not face these NAT traversal challenges because the CE router has a public IPv4 address or the ISP controls the NAT behavior. 6RD is much simpler, more reliable, and provides better performance than Teredo for ISP-managed deployments. Deployment considerations and best practices. Successfully deploying 6RD in a production environment requires careful planning and attention to several important considerations. While 6RD is relatively simple compared to some other transition technologies, there are still potential pitfalls to avoid and best practices to follow for optimal results. The first major consideration is sizing your IPv6 prefix allocation appropriately. You need to think about how many customers you will support, how much address space each customer should receive, and how to embed the IPv4 addresses efficiently. If you have a large contiguous IPv4 block, you can use IPv4 prefix compression to reduce the number of bits needed for embedding, which leaves more bits for customer subnetting. For example, if your IPv4 block is 203.0.113.0/24 and you set the mask length to 24, you only need 8 bits for embedding. Combined with a /32 6RD prefix, this gives you plenty of room to allocate /56 or even /48 prefixes to customers, allowing them to subnet their networks extensively. MTU handling is another critical consideration that is often overlooked. When you encapsulate an IPv6 packet inside an IPv4 packet, you add 20 bytes of IPv4 header overhead. If the original IPv6 packet was already at the maximum transmission unit size of the underlying network, typically 1,500 bytes, the encapsulated packet becomes 1,520 bytes and will not fit. This leads to fragmentation, which hurts performance and can cause connectivity problems with sites that block ICMP. The best practice is to configure the CE router to advertise a reduced MTU to customer devices, typically 1,472 or 1,480 bytes for IPv6, which ensures encapsulated packets stay under 1,500 bytes. Alternatively, if you control the entire network path, you can enable jumbo frames or increase MTU throughout your infrastructure. Security is an important aspect that requires thought. 6RD itself does not add significant security vulnerabilities, but you need to ensure that your border relays properly validate traffic. The relay should verify that incoming IPv4 packets actually contain IPv6 payloads and are not attack traffic. It should also implement anti-spoofing measures. For outbound traffic from customers, Verify that the source IPv6 address matches the expected 6RD-derived prefix for that customer's IPv4 address. For inbound traffic from the Internet, ensure the destination IPv6 address is within your 6RD prefix range. Rate limiting on the border relays can help prevent resource exhaustion attacks. Monitoring and troubleshooting capabilities should be built in from the start. Your border relays should log statistics about encapsulation and decapsulation operations, track error conditions like MTU issues or invalid packets, and provide visibility into traffic volumes per customer. On the CE router side, customers or support staff should be able to verify 6RD configuration, see the calculated IPv6 prefix, and test connectivity through the tunnel. Tools like ping and traceroute need to work correctly through the 6RD tunnel, which requires proper ICMP handling at the border relay. Setting up these operational capabilities before you have customer-facing problems will save significant headaches later. Practical configuration example. Let's walk through a practical configuration example to see how 6RD is actually set up on both customer equipment and provider border relays. This will tie together all the concepts we have discussed and show you exactly what configuration is needed to make 6RD work in a real network. We will look at configurations for common platforms and the DHCP option distribution that makes it all automatic. On the customer premises equipment side, we will use a Linux system as an example, since it clearly shows all the parameters. The IP6RD kernel module needs to be loaded. Then, we create a 6RD tunnel interface. The key parameters we need are the 6RD prefix, which we will set as 2001:DB8::/32. The IPv4 mask length of 24, indicating our common prefix. The relay IPv4 address, which might be 198.51.100.1, and our own IPv4 address, which could be 203.0.113.45. The configuration commands would use the IP tunnel add command to create a tunnel named 6RD with mode SIT. This also involves setting the local IPv4 endpoint and configuring the 6RD prefix and 6RD relay prefix parameters. Once the tunnel interface is created, it needs to be brought up and configured with the appropriate IPv6 address. The CE router calculates its 6RD IPv6 prefix based on its IPv4 address and the 6RD parameters. It then assigns itself an address from this prefix, typically using :1 as the interface identifier. It also needs to enable IPv6 forwarding so it can route traffic between the customer's internal network and the 6RD tunnel. Finally, it should run a router advertisement daemon like RADVD to advertise the IPv6 prefix to devices on the customer's LAN, allowing them to auto-configure their own IPv6 addresses. On the border relay side, the configuration is more straightforward in some ways, but it requires more robust hardware. The relay needs a native IPv6 interface connected to the Internet and an IPv4 interface facing the provider network. You configure a 6RD tunnel interface that is set to accept traffic from all customer IPv4 addresses within your allocation. The key difference from the CE configuration is that the relay needs to handle traffic from multiple customers, not just one. It routes the entire 6RD prefix, 2001:DB8::/32 in our example, through the tunnel interface, which tells it to decapsulate any IPv6 traffic destined for addresses in that range. The beauty of 6RD is that customers do not need to manually configure these parameters. They are distributed automatically through DHCP option 212, which is specifically defined for 6RD. The DHCP server at the ISP includes this option in responses to customer requests. Option 212 contains the 6RD prefix, the IPv4 mask length, and one or more border relay addresses. When the CE router receives this DHCP response, it automatically configures the 6RD tunnel with these parameters. This zero-touch provisioning is one of 6ROAD's major advantages. Customers get instant IPv6 connectivity as soon as they connect to the network, with no manual configuration required. Future of 6RD and migration strategies. As we conclude our exploration of 6RD, it is important to understand where this technology fits in the broader context of IPv6 transition and what the long-term migration path looks like. 6RD is fundamentally a transition mechanism, designed to be used temporarily while networks evolve toward native IPv6. Understanding its role in this evolutionary process helps in planning deployments and setting realistic expectations. 6RD is most valuable during the middle phase of IPv6 adoption. In the very early stages, when an ISP has no IPv6 deployment at all, they might start with simpler solutions or focus on upgrading key infrastructure first. 6RD becomes attractive once there is management commitment to IPv6 but the core network is still IPv4 based. It provides real, production-quality IPv6 service to customers without requiring a complete infrastructure overhaul. This allows the ISP to gain operational experience with IPv6, satisfy customer demand for IPv6 connectivity, and generate business justification for future investments. The natural evolution is from 6RD toward native dual-stack deployment. As routers in the core network are upgraded or replaced, they are configured to run both IPv4 and IPv6 natively. Once enough of the network supports native IPv6, the ISP can start migrating customers from 6RD to direct IPv6 connectivity. This might happen in phases, perhaps business customers first, then residential. During this transition period, some customers might still use 6RD while others have native IPv6. The flexibility of 6RD makes this mixed deployment quite manageable, since it can coexist with native IPv6 without interference. Eventually, as native IPv6 deployment becomes comprehensive, 6RD can be phased out entirely. At this point, the ISP might even flip the model and use DS-Lite to carry legacy IPv4 traffic over an IPv6 core, while IPv6 runs natively. This represents the final stage of transition where IPv6 is the primary protocol. The timeline for this evolution varies enormously by provider. Some might move through these phases in a few years, while others might take a decade or more depending on their infrastructure, customer base, and business priorities. What makes 6RD particularly valuable is that it does not lock you into a specific long-term architecture. It is a tool that serves a specific purpose during a specific phase of network evolution. Thank you for your attendance. Please consider subscribing to the channel.